This is the last course on Birkhoff section and contact flow. So let me remind a bit where we stopped on Tuesday. So the setting was of a compact three-manifold with no boundary, oriented. There is a non-singular flow in it, so there were a lot of contact flows and in particular rep flows. Here I give a general definition, which will also work for another flow, say. So there are two definitions. There is the definition of a transverse surface, which is a surface with boundary, whose interior is transverse to the vector field, and whose boundary is tangent to the vector field. So one question one might often ask, but maybe you already know the answer, is how are these two conditions compatible? In particular, how do these surfaces look around the boundary? And so here is what it looks like. For example, if you have a periodic orbit gamma in the image of the boundary, and well, for simplicity, assume it's hyperbolic, like it will be the case for another flows. And so, how this may look around gamma? So here is in the white thing here is gamma seen as a vertical line. Here is the hyperbolicity, so you see that there is the stable and the unstable manifolds around gamma. And so there are, roughly speaking, four possibilities. In a sense, the most common ones are those two. What you see here is that the transverse surface here in purple is like a helix that rotates around the periodic orbit. And if you think about it, this helix is transverse, the interior, I mean what is outside the vertical line, the rest is transverse to the vertical direction, so it has good chances of being transverse to the flow. Yes. And it rotates like that, so it's like a staircase, a helicoidal staircase. The boundary is vertical, but the staircase itself is transverse to the vertical direction. So here is a staircase just rotating in the other direction. And actually there is another possibility that is in a bit specific to hyperbolic orbits. That is that actually the surface may also be vertical in one quadrant delimited by the stable and unstable manifolds. Because if you look at this yellow page here, actually the vector field comes from the front and goes to the right, so it's indeed transverse to the vector field. Yes. Okay, here is a bit of additional information is that you can add some. There are some natural orientation issue and question, and this gives nice information. So the surface, as we said, is transverse to the flow, so it's oriented and it's transverse to the flow. So when you flow, you cross it positively. So this induces an orientation on the surface, which is drawn here, maybe a bit too small, but so with the screwdriver rule, you have an orientation on the surface. And so on the boundary orbit, this orientation of the surface induces an orientation on the boundary. And if you look carefully here, you see that on this picture, the induced orientation of the surface on the boundary goes actually to the bottom. Here you see that the orientation with the screwdriver rule is rotating like this. So if you look at the boundary, it's going downwards. Okay, so that's why I would say that this is a negative boundary component. And well, since around each point in the boundary we just see one page coming with a negative orientation, we will say that we have multiplicity -1. On this picture, on the other hand, the orientation is still given by the screwdriver rule, but since, well, actually you see things in a mirror, the orientation you see on the boundary here is positive. If you follow the screwdriver rule, you go to the upward. Hence, we have a positive orientation, say, and, well, if I see one page here, I will say that the multiplicity is +1. Okay, and if you play the same game here, you see that this one has multiplicity +1, and this one has multiplicity -1. Okay, you may ask why do I say multiplicity, because this is just plus and minus ones, because I will just mention it quickly, although it's not that important today, because of the fact that actually here the surface may appear several times. So the picture you may see may be a bit more complicated in the sense that here, for example, you may have several staircases rotating like that. So if you have two parallel staircases that never meet, well, then you would say that in this case, you would have multiplicity -2 because around every point here in the boundary orbit, you see two pages, you see your Birkhoff section twice, one from each side, with multiplicity -1, so this is -2. Okay, just a remark here. Yes, actually, yes. I didn't say whether these two things were actually the same boundary component, winding several times, or just two different boundary components coming here. I don't really care. But yes, that's a good point. So if you want to have a complete information, your multiplicity should be something a bit more complicated, telling you how many boundary components you see and how many times they wind here. Just one last remark here is that actually these four possibilities are not totally mutually exclusive in the sense that these two may coexist. Yes, because you may have this in one quadrant and this in the other quadrant. On the other hand, if you have this or this excludes everything else. Okay. Yes, and so the third condition, the most interesting thing, is that if you have the third condition, that the surface intersects all orbits of the flow in finite time. In this case, we call that a Birkhoff section. Yes, and so, well, it's you have to check. So, just to comment that here, here you see that around the boundary component, the first return time on the surface is bounded, because basically the first return time is the time you need to go from one stage to the next stage of your helicoid. Yes, here it's the same, but here the first return time is not bounded, because if you take orbits that are closer and closer, say, to this blue stable manifold, they all intersect this orbit, but it takes longer and longer time because they follow gamma for a longer and longer time. So here the first return time is not bounded. Hence, what you see here is a transverse surface, but not a Birkhoff section. So these two are not mutually exclusive, but on the other hand, they don't appear if you have a Birkhoff section. Okay. And I finished with last time with one example, which was the geodesic flow on a sphere here. So I explained that when you have a simple closed geodesic on a sphere, like here, like that one, in the unit tangent bundle, so the bundle made of the fibers of those circles here, you may consider the set of tangent vectors pointing to one side of the geodesics. So here in red, you take all these arcs here, which corresponds to the vectors pointing to the right. In the unit tangent bundle, this defines you an annulus. Yes, and this annulus is a transverse surface. Actually, if you think about that annulus, and if you imagine that this orbit is hyperbolic, which is not the case on the picture, you would rather take that one. The picture you see actually corresponds to that picture. Yes. So this is an annulus, and in general, it's a transverse surface because it doesn't intersect every one. For example, this annulus here doesn't intersect the lifts of those two periodic orbits, or on any orbit that stay on one side of the geodesic. So there is one nice case in which it is indeed a Birkhoff section, is if the sphere is positively curved. It's like a potato. On a potato, this hemisphere here, this Birkhoff annulus here intersects every one, so it's a nice Birkhoff section. But in general, it's not the case. So let me now just complete a bit this example by considering the geodesic flow on a hyperbolic surface. So sigma, oh no, sorry, S. So, if you take a nice hyperbolic surface, you may want to construct a Birkhoff section in this case, and maybe the most natural idea so far is to export what we know how to do here. So, can we take Birkhoff annuli? Well, for sure we can, because there are many simple closed geodesic on a hyperbolic surface. So, for example, you can take that one, and then you take that one, and then you take that one. These are nice Birkhoff annuli. These are nice simple geodesics, so you take those Birkhoff annuli here, you choose one direction, for example that one, and you wondered, is it enough, does that work? Well, this is a disconnected transverse surface here, and does it intersect all orbits? Well, it intersects a lot of them, but not all, because there are some orbits that could stay in one half of this surface, so you need to add some other things. So for example, you may add some other closed geodesics here. And, in a sense, I can add a sixth one. So you may wonder, why do I take those geodesics? This choice is not that important. What is important is that I will take here, I consider, well, say 6 geodesics, gamma 1, gamma 2, gamma 3, etc., gamma 6. Yes. And so I can consider some Birkhoff analysis along this, around these geodesics. So I can consider the union A gamma 1, union A gamma 6. And I may wonder, is this a Birkhoff section? The reason I took that many geodesics is it because here I am sure that all geodesics, all orbits of the geodesic flow will intersect those curves in finite time. Actually, if you cut the surface along what I drawed, you see 6 hexagons. And so, well, if you deploy things in the hyperbolic plane, this is what you see. Yes. So basically, if you cut along some of these geodesics, four of these geodesics, this is the picture you see. And so, well, you have gamma 1, gamma 2, etc. And so any geodesic in the hyperbolic plane will intersect those geodesics at some point. Okay, but is this really a Birkhoff section? The point is that, well, I have annulus, but now they intersect. So I have to understand what happens here. So what happens here? So I have a double point. I have 2 geodesics intersecting, and I'm considering these Birkhoff analyses here. So in the unit tangent bundle, what do you see? Well, first you have to lift these 2 geodesics. In the unit tangent bundle, they lift to 4 orbits of the geodesic flow, which look like this. So here is, I will draw the fiber. Here, if you have this double point here, the fiber is somewhere here. So you see that, well, in the fiber, there is these tangent vectors, then there is that one, then that one, and then that one. So I have, and here I see these 2 Birkhoff analyses. So in red, this corresponds to this surface here between those 2 orbits. And, well, I can draw the other one in another color. And if I look at that one, it corresponds to Birkhoff annulus between those geodesics. And what do you see here on the picture? You see that actually those 2 annuli, they intersect along an arc here. So it's not exactly, you see that the interior of the surface is not transverse to the geodesic flow. But what is nice is that if you look around that arc, what you see is that you see, say, a certain piece of surface. Here is the arc, and here is the other piece of surface. So this is what you see along the intersection, and everything here is transverse to the geodesic flow. So there is a flow here that is transverse to both surfaces. And so what you can do here is, in a sense, is to resolve this arc. So you desingularize this arc, and you see something that looks like this. So here the green arc is not anymore here, but I resolved in transversally to the flow. The flow tells me how I have to resolve that. In a sense, anyway, the surface were oriented, and I take the unique resolution that preserves this orientation. So if you do that, well, actually on the picture, what you will see here is that you remove this arc, and in a sense, you open up a bit. This is what you will see here, that you have this arc here, and here they are connected, like you go from the red surface to the purple one, and here from the purple to the red in the back. Well, it takes time to integrate this picture, of course, but you can trust me. Okay, and so the statement, so this operation, so the operation of if, say, sigma 1, sigma 2 are transverse for for mx, m phi t. Their Fried sum, I will call that the Fried sum because David Fried used it and introduced it and used it in 1983. Is obtained by, okay, first you have to put them in transverse position, in, well, generic transverse position, and also transverse to the flow. Yes, take the union. Yes, and desingularize the intersection. The intersection. Okay. Yes. Yeah, exactly. Yes, yeah. It's just in general. Well, you put that, but well, in all my pictures, they are already in a good position. Yes, and so this gives something that I will just denote. Well, the Fried union of sigma 1 and sigma 2. Okay, and the claim here.
What happens to the boundary when you desingularize?
Oh, that's a good question. I don't know whether I want to answer it, but yes. No, well, what happens is nice. There are several possibilities because actually I didn't really say anything about the boundary of sigma 1 and sigma 2, whether they have or not common boundary component. So let's assume that I am on the boundary component of one but not the other. So what you see in that case, if you are in the boundary of one but not the other, yes, these are my colors. So, well, locally what you will see is this. There is one page here, which is, yes, and the other one, well, it just, this gamma is not in the boundary of the other one. So the other one looks like a disk locally here. And the intersection here is an arc like that. And so what you will see is a picture that actually Anne did is that, so what you will see is actually that the sum will be like a helix here that will rotate. I don't know whether I can draw it, but okay. The sum is something like this, and then it starts rotating, and then you are back to the red one. It's not very nice. If you want, one thing you can do to picture better what happens here is well, what I like to do is to blow up the boundary. If you blow up the boundary, so which means that you blow up gamma. So this is the blow up of gamma. So if you blow up gamma, you see that the red page here was just arriving like this. Yes, and it was co-oriented. I didn't put, but there is a co-orientation here given by the flow. Okay, and the purple guy here comes like that. It's also co-oriented. Yes, and so what you do on the boundary is basically that you also resolve this intersection transversally to the co-orientation given by the flow. So here you just resolve this like that. So you see that now it's a helix. Okay. So well, something I didn't say, I could say, but well, I will just say it orally, is that this boundary issue you have to be a bit careful. So there are two ways to deal with this boundary issue. Either you take this general definition and you have to work and check things every time, or you take a stronger definition in which you ask that actually you can blow up the boundary and the surface compactify nicely to a curve on the boundary. If you add this extra condition, then you say that your section or your surface is delta strong, and in this case everything behaves very nicely. So that's what I like to do. But of course, well, you have to be sure that you can do that. Okay, so just the claim to finish the theorem, so which is due to, well, the construction, actually this construction here was more or less introduced by Birkhoff in 1917, and it was rediscovered by Fried in 1993. I mean, Fried did read Birkhoff, and so he said it's due to Birkhoff. And so the theorem in that case is that here, this union here, A gamma 1 union desingularized A gamma 6 is a Birkhoff section for the geodesic flow. Yes. Okay, and I will just add, well, two remarks. Well, the most important, maybe the first remark is that, well, as is more or less explained here, when you do that, the multiplicity and the boundary component behave additively. Yes, so multiplicities on boundary components add up. Yes. And the second remark that I will do is that actually the Euler characteristic also behaves very well like that. So it's not exactly the Euler characteristic, but I would say the punctured, well, it depends what you call the Euler characteristics. The punctured Euler characteristics add up also. So what do I mean by punctured Euler characteristic? It means that, well, here this surface, they are surface with boundary. So you may just consider the standard Euler characteristic. But here, when I take the union, you see that there was something that was not in the boundary of the purple surface, but that is now in the boundary of the union. So when I say punctured, it means that from the purple surface, I will remove its intersection with the boundary of the red surface. Yes? If you do that, then the Euler characteristic behaves additively, which is very convenient when you do this construction to check the genus of what you obtain.
So just for this case or in general?
In general for the Fritz sum, sorry. Okay. So in particular, I can say that if you consider these annuli here, you have that the Euler characteristic of an annulus, well, you know that the Euler characteristic of an annulus, you know, but I have to check, yes, is 0. Yes. But so now if I consider the punctured Euler characteristic, you see that actually each of these annulus here intersects some boundary orbits of some other annuli here. So what happens is that actually the picture you see here, if you look at A gamma 1, the annulus A gamma 1 is an annulus. But actually, you have to puncture twice because here there is the intersection with A gamma 2, say, and here there is the intersection with A gamma 6. The boundary of A gamma 1 and the boundary of A gamma 6. So that's why the punctured Euler characteristic here is -2. And hence, the punctured Euler characteristic of this Birkhoff section is -12. Yes? And, but what you can check also is that this surface, what is the number of boundary component of this surface? Well, where do the boundary component come from? Well, they come from the boundary component of the annuli. At each annuli, there are 2 boundary components. So 2 times 6 equals 12. And from this, you deduce that the genus of this thing is 1. So this surface here is not that complicated, it's just a torus. So here, this geodesic flow admits a Birkhoff section, which happens to be a torus. Okay. A remark to connect, since now we spoke a bit about multiplicities, is that, so first a remark is that when sigma, say d sigma, is a Birkhoff section, and if all multiplicities are, say, plus or minus 1, then what you can do is you push sigma along the flow by pushing sigma. Sorry, yes, okay. We have very good relations, but we don't have the same notations. Sorry. So when sigma is a Birkhoff section, by pushing sigma along the flow, by pushing sigma along phi t, you describe you describe an open book decomposition of M. Yes? So here, Anne was a bit restrictive on what you can see on the boundary because she said that a page of an open book decomposition has to come once along the boundary. On the other hand, well, if you care about open book decomposition, whether it's +1 or -1 was not really, yes, the boundary was not really oriented in what she said, so plus or -1 is okay. But now, if moreover, if you consider a red flow, now if sigma d sigma is a Birkhoff section for a red flow, so R alpha, yes, and if all multiplicities, and here I have to care, so actually, well, okay, -1, here I am a bit sorry, but here it's -1, then, well, by pushing sigma along the flow, by pushing sigma, you describe an open book decomposition of M adapted to R alpha, which means carrying adapted to the contact form, to the contact structure. Yes. So in a sense here we can reflect, we can rephrase Giroux's theorem. So this is just the rephrasement of Giroux's theorem, is that for all psi a contact structure, there exists alpha a contact form such that R alpha admits a Birkhoff section with multiplicities -1. Okay, I will not say, so of course it's not at all like that Giroux constructed it. But it's one way to rephrase the theorem to make the connection here. Yes? Yes. Yes. But of course, it's not at all the way she described the proof, and it's not at all how it was done. It's just a reformulation of the statement, but if you want to prove it, it doesn't help. Yes. So where am I? Okay, I just want to prove, yes, I just want to sketch actually the main theorem of Fried in 1983. Now let's, so I described Birkhoff sections, I described some examples which turned out to be Hausdorff flows. And this theorem tells you that in the world of contact structure, well, you have some nice Birkhoff section in a sense. But in the world of Hausdorff flow, it's even, I would say, easier. Maybe we can discuss that, but yeah, I think it's easier. So here is the theorem by Fried in 1983, that every transitive Hausdorff flow admits a Birkhoff section. So the construction I did here for the hyperbolic flow on a hyperbolic surface, in a sense, well, it's a particular case of this theorem. So it's not really a particular case because the construction is much less explicit here, but I will still sketch the proof. Okay, I will sketch the proof, but I will start from something that is really important and not that trivial. It's a theorem of Ratner, of Marina Ratner from 67 or 8, that say that transitive Hausdorff flow admits Markov partition. So I will not exactly define a Markov partition, but what it means is that, in a sense, there exists a collection, say R1, Rn, of rectangles transverse to the flow, transverse to say, the vector field, intersecting all orbits. And, well, actually, you would need maybe a bit more than that, but, the Markovian property is not that important here. What is important is that you intersect all orbits. So, here is an example of such a rectangle here. So, you have a rectangle that I drew in brown. So, it's transverse to the flow. So, in particular, it's transverse to the foliations, to the two-dimensional invariant foliations. So on this rectangle, you can draw the intersection of the unstable manifold with the rectangle and the stable manifold with the rectangle. So this is a rectangle which is bifoliated, but it has some boundary. But here I don't ask anything about the boundary. I just look at the interior of the rectangle, which is like a local transverse surface. Okay. The fact that the flow is transitive implies that periodic orbits are dense here. So everywhere in this rectangle, there are periodic orbits. In particular, near the, say, bottom left corner, I can find the periodic orbit alpha. And near the top right corner, I can find another periodic orbit beta. Okay. So now I draw a rectangle of a certain width here, and that goes up to the back of the surface. So here I draw, this is a rectangle in a sense that is just made of, its boundary is parallel to the Anosov directions. So I look at R alpha, and I push this rectangle along the flow, yes, and I push it until alpha comes back. Alpha is a periodic orbit, so after a time, which is its period, this corner comes back to here, and so if you push the rectangle by approximately this period, you come back here, so up to a small row. If you push this rectangle by the flow long enough, its image is something like that. It's like that because the stable direction is contracted. So this was long, but now it becomes short, and this was short, but in the unstable direction, so this becomes long. Yes. So the image of R alpha by pushing along the flow is something like that. Okay, I play the same game with the periodic orbit beta. So beta, I put a rectangle that is small in this direction and goes up to this boundary, say, and I push it for a period which is approximately the period of beta. Yes, so you push it and you see this rectangle here. So now applying playing the usual Anosov game, if you look at this intersection here, if you push it by this thing here, it comes to something that is, so it was going from the left border to the right border, so it goes onto something like this. Yes? But now you consider how the intersection here, and you push it now by, like R beta, you follow what happened here, and it gives you something that is even smaller here. Okay? And so somewhere here in the intersection, there is a fixed point obtained by following first alpha and then beta. Okay. So there is a fixed point, which means that if you first follow alpha, this point comes to somewhere here, and if you follow beta, it comes to somewhere here. In particular, now if you follow the flow, if you do the 3D picture, what it means is that I call this point here alpha beta. Yes. If you follow this point, so it will follow an orbit, and in particular an arc here connecting those 2 points, it will be an arc here that will describe a certain ribbon. And this arc here, after pushing by this time approximately, it comes back to this arc here. And similarly, if I take the yellow chalk, if you take this arc here, this one connecting beta to this point that I call beta alpha, you push it along the flow, you push it, and as we said, this point here, this segment here, comes back to a segment somewhere here. So it comes back to something behind. So in this way, in the 3 manifold here, I describe a certain surface. So if you compute carefully, you see that it's a pair of pans. It's a 3-punctured sphere, which is made of 3 things. There is There is actually what comes from the rectangle here, which is transverse to the flow, because it's a part of a rectangle that was transverse to the flow. And then I have these two annuli, which are tangent to the flow. Yes, and so the thing is that when you have a flow, and you have a surface that is somewhere transverse and somewhere tangent to the flow, well, maybe like that, actually you can smooth it to be transverse to the flow. So if you have this surface which is a bit topological, if you smooth it, you can make it completely transverse to the flow. And so this gives here what I will call P alpha beta, a transverse pair of pants. Yes.
You're doing this preserving the boundary which stays tangent.
Yeah, exactly. Yes, sorry, yes. So the interior is transverse, but the boundary is made of 3 periodic orbits. If you check the multiplicities, well, I didn't do it, so.
Is it possible to get it embedded?
Ah, a good question. I will not answer that question. No, I mean, yes. No.
Alpha is periodic, it can cut the rectangle.
Exactly. Alpha could cut the rectangle many times. So what you can make it periodic if you are sure that inside this rectangle, alpha and beta do not come back. But of course, I mean, you can do it, but then you decrease the size of the rectangle. And so, yes, it's possible to make it periodic, but then it intersects many less orbits. So I am not really happy with that. But yes, you can do it embedded. The problem is that you will reduce the number of orbits you intersect.
You can choose alpha cutting just once.
No, but I mean, if alpha cuts many times, you take one. You take, say, the rightmost and topmost intersection. Hmm? Yes, yeah. No, I mean, it's not completely trivial, but yes, you can. I'm not claiming that for any pair alpha beta you can do it. I'm not claiming that. I just claim that you can make this construction with some alphas and some beta to have it embedded. I'm not claiming it works with any alpha and beta. Yes. Okay. Yes.
Can you do like something like, I don't know, about like having a transverse and a tangent surface, making a transverse surface? Is there something more general besides this?
Yes, I guess so. I will not risk to give a statement, but I am sure there is one. Yes. Okay, and so just to finish the proof, well, I will just go very quickly, but basically, if you take, so in this way, P alpha beta is a transverse surface, but it's not necessarily a Birkhoff section because it's not clear it intersects all orbits, and it has good chances not to intersect all orbits, exactly like the annuli we had before. So this is something that intersects some orbits, but not all of them. But just I said that there is a finite number of rectangles, and you see that here this surface intersects almost everybody in this rectangle, except maybe along the boundary. So, well, I will go a bit fast on this, but then there is the fact that there exist finitely many P alpha I beta I, such that the union of all these things intersects all orbits. Hence, it is a Birkhoff section. Yes? Yes. I mean, here I take the Freed union. So I have many intersections to resolve. Yes? Yes. Oh, yeah. Yes, you are right. Yes, actually, Christian, well, I can make it embedded, but it's not anymore a pair of pants. Because it self-intersects itself, but you can resolve these self-intersections. Yes. So, yes. No, it's just, okay, from this proof, if you want to control the genus, well, good luck. Well, I didn't really try. I'm not sure someone really tried, but yes, it's very complicated to control the genus from here. Okay, so where are we now? Well, where are we now? Now I will just survey some results Yes, just one remark here is that if you look at the boundary components, the multiplicities, they alternate. So in this construction, with probability 1/2, these are the multiplicities. I mean, sorry, I didn't prepare that, so maybe it's +1 and -1, but I don't, yes, okay. So you see that in particular, you have positive and negative multiplicities. So with this respect, it's not that good, this construction. Yes. But for just constructing Birkhoff section and so on, it's good. Okay. Yes, so now I want to make some connections between these two worlds of red flows on one hand and another flows on the other hand. So just a map of this world here. So if you look at the world of three-dimensional flows, there are two classes that you may like. I mean, at least if you are here. So of course that one, you are not allowed to say you don't like it. So these are the another flows. So among the another flows, first there are the non-transitive ones. Yes, well, I don't really know them, but they exist. And there are the transitive ones. Okay. And then there is the world of rep flows, or a bit more generally contact flows, but let's stick to rep flows, okay, which are here. Okay. So in the world of rep flows, there are some particular cases, a subclass which is made of the geodesic flows on unit tangent bundles, so as Anne explained. So this is a subclass. Yes. And in the world of another flows, there are two particularly simple classes, which are the suspension flows. So the suspension flows, we didn't speak that much about them this week, because they are supposed to be almost trivial. This is the flows you obtain by taking a hyperbolic matrix acting on T2 and suspending it. So this is a certain class. Actually, they are not reb, so they lie here in another transitive another flow, not non-reb. In the intersection, there is the nicest flows, which are the geodesic flows on hyperbolic surfaces. Yes. Just one parenthesis that we already consider surfaces, but you may consider also orbifolds. Well, so just quotient of the hyperbolic plane by Fuchsian groups. So they are here. And so, well, in this picture, so there are another flows which are not necessarily on hyperbolic surfaces, but there is a bit of positive curvature somewhere, but still the flow is another. This is a mysterious world to me. Okay. And then you see that there is an intersection here between those two classes, constraining the geodesic flow, which is what are called the Reb-another flow, or as Thierry called them, the Reban flows. So these are the cool guys. Yes? Okay. So this is one thing. Okay, and you may think, what can we say about Birkhoff section in all this world? Yes. So I would say, since we introduced Birkhoff section, I will raise a few questions about Birkhoff section. Given a flow, the first natural question is, does your manifold with your flow admit a Birkhoff section? This is a natural question 1, and I will just... a second question, assuming you may answer the first one, and inspired by this construction here. Here, no hypothesis. It's a general question. The hypothesis you want. Okay. Oh, sorry. The second question, assuming you know there is a Birkhoff section, does M phi t admit a simple Birkhoff section? And what I mean by simple is low genus. Because I am a topologist, so I like low genus surfaces. So for example, here I had genus 1. I was happy. Yes? Okay, I will just, okay. And I will ask, say, a third question, which is given, it's more a problem, given a Birkhoff section, well, or using Birkhoff sections, say something interesting. Okay, So let's review a bit what is known on these three questions concerning these different classes. So if you look at, okay, maybe I will take a bit more space. Yes?
Simple Birkhoff sections are always considered to be low Birkhoff sections. But why aren't you interested in the number of boundary components? I mean, for another language.
Yes. In general, I don't know. Okay. I mean, well, in a sense, I mean, if you have really low genus, say genus 0 or 1, say genus 0, there are more results on dynamical on the first return map on a 0 genus surface than on a high genus surface. So in a sense, if you want to use Birkhoff sections to say something about the dynamics, it may or may not, depending, help to have a low genus surface. That is one possible answer, maybe not the only one. Yeah.
There's a result from collaborators that said that Webflow and WhisPeer may have arbitrarily large number of minimal boundary components.
No, I mean, that's a perfectly valid question. You could replace low genus by, for example, small number of boundary components. That is also valid. For some reason, I prefer that one, but yes, you can ask the other one. What's the minimal number of boundary components? For another flow, no, but you will. But you know why? No, yeah. It's not always one. Yes, so, okay. So, first, if you ask for general rep flows, first I will take a more general class, which is rep flows up to changing the contact form. So what it means you consider really a contact structure, yes, and you consider the set of all rep flows for this contact structure. And so the reason why I say that is that then the answer to question 1 is yes by Giroux's theorem. Yes, Giroux's theorem tells exactly that if you are allowed to change the contact form, so picking your favorite rep flow for a given contact structure, then the answer is yes. Okay. And now if you go to question 2, does it admit a low genus Birkhoff section? Here I will just say for those who know, that the answer is if the structure is what is called over-twisted, it's a topological property, the answer is yes. So it admits Birkhoff section with genus 0. This is a theorem by Etnayer. Yes. And if psi is what is called tight, then it's an open question. And I think that the experts expect a no answer. But yeah, that's a question. Okay. So if you take rep flows without really rep flows, like you fix the rep flow, here the answer is, well, generically yes. And for this, I am sorry, you will have to come tomorrow at 8:35 sharp to get something. Yes, but the answer is generically yes. I can say that it has been proven recently by Contreras, Mazzucchelli, and there are 2C as well, and Colin. Yes. Okay, so it's something a bit complicated.
Suppose you were tight for the question 2 for tight, so you said it's
Yes, expected no. So it means that you expect to be able to, you expect to find a contact structure that admits no supporting open book decomposition with genus smaller than 10, than 100, I mean for any G. For any N, you expect to find one that doesn't admit any open book decomposition with page has genus smaller than N. This is the expected answer, but I think it's considered a hard question, so it's advised not to look too intensively into that one, from what I understand. Okay. And now, if you go to another flows, so the answer is yes, every another flow has a transitive. For non-transitive one, the answer is no, but I will stick to transitive. The answer is yes. This is the theorem of Fried. Yes. And here, well, there is a question mark. It's a question that Fried is asking. Yes, and it's motivated by the fact that the answer is yes for the geodesic flow, but it's still an open question. It's, I think I can say it's my favorite open question. Yes, that's why I wrote the question in this form. And just to, if you look at, yes, I just wanted to say if you look at geodesic flows on hyperbolic surfaces, so the answer, and even orbifolds, yes. Yes, the answer is yes here, and the answer is yes here. So it was proven by Fried for surfaces, and actually it was proven with well, we proposed a construction with Mario Shannon for orbifolds. Okay. Yes. Sorry? Yes? Yes, you mean it in general it's at least 2 boundary. Yeah, well, actually I will speak about the number of boundary components now. I mean, the boundary. Okay, so now I would like just to give one answer to question 3. I was planning to give 2, but realistically it will be 1. Okay, so if you yeah, okay, I will just erase it. So I don't know if you remember, well, probably you all remember, there is a trichotomy concerning another flows. So a transitive another flow, there is the trichotomy due to Barbeau and Fenley, that if M phi t is transitive another, oh, maybe I don't have to put transitive, but I will put it anyway. Okay, then either, if you look at the leaf space, then the associated bifoliated plane looks like, so either R2 with its trivial foliation, yes, in which case actually, which by a theorem of Solodov is actually equivalent to M phi being the suspension flow of a hyperbolic matrix. So it's not that trivial, the theorem, but it's true. So if the bifoliated plane is trivial, you have that. Okay. Either it looks like, say, this thing, which is called R-covered skewed. Yes. And here you may wonder, do I have other ways to write it? Or I would say the rest, which is called non-R-covered. And we have heard about these things already a lot. Yes. Okay. And so here, yes. So here you see that in the first case, it means that the flow is actually, saying that the flow is a suspension flow, means that actually you can foliate the manifold by Birkhoff section with empty boundary, because you just take the torus here, you push it by the flow, and so you foliate by Birkhoff section with empty boundary. So here, it's equivalent to the existence of a Birkhoff sections sigma with empty boundary. Okay. And so we say that all these flow, this transitive one, here they all admit a Birkhoff section. So you may ask, can I say something interesting about the Birkhoff section? And here is the nice theorem. So this theorem was proven by Theo Marti, and Christian gave an independent proof, and Asaoka gave a third independent proof, all around 21. Yes, that actually this thing, you can characterize it using Birkhoff section by the existence of a Birkhoff section with multiplicities. With multiplicities of constant sign. Okay, I say of constant sign because here it can be covered skewed in one sense or the other sense, and the sign here corresponds exactly to this sense. So in particular, if you think about the geodesic flows, the Anosov geodesic flows here, I said, no, I didn't say, but the boundary multiplicities are all -1. Yes? And the fact that it exists a Birkhoff section with all negative multiplicities, in a sense, tells you through this theorem that this flow is R-covered skewed. Well, of course, you don't need this theorem to say it, but okay, it's an illustration of this theorem. Okay, and so, well, here you can say that, well, thanks to this theorem, this is equivalent to, for all Birkhoff section, sigma. The signs are mixed. Multiplicities have mixed signs. So in particular, to answer your question, Thierry, or your remark, you see that in this case, there cannot be only one boundary component because you need to have at least two opposite signs. So, yeah. Actually, you can enforce this theorem, correct me if I say wrong, exactly to say that in this case, you can even build a Birkhoff section with only one boundary component. So in a sense, if you think about your remark that you may want to minimize the number of boundary components, you could say that this is minimal number 0, minimal number 1, and minimal number 2. Yeah, that's another way of putting it. Okay. And another remark using that, we'll continue here, is that you make, so this is a very nice trichotomy. Yeah. Yes?
When you say number 2,
it's not obvious.
You mean for every non-orthogonal zone, you can have a Birkhoff section with 2 boundary components?
Christian, Theo, is it right or not? Yeah, I think it's true. Oh, yes, sorry. Yeah, so sorry. Yeah. Okay, so minimal number 1 is here. That's here minimum is 2 is non-trivial. And come this afternoon. Yes. Okay. And so this is okay. I like this theorem because it. I mean, for a long time I understood nothing about this thing, but this I can understand. So at least now I understand this trichotomy. Now you may think how this trichotomy here interact with this picture here. In particular, you see that we have the suspensions here. We have the transitive non-reb and the transitive reb. Yes, and so there was a theorem by Barbeau in 2001, I guess. Yes, that if say M phi x is reb Anosov, then actually it's R-covered skewed. So you know that these guys here are included somewhere in the R-covered cube. And so you may wonder whether this is really the same or not. And it was a question asked by Thierry. And now, well, I can advertise that here, this is also a theorem by Theo, that actually, well, actually it's a converse implication. The answer is yes. So here, this thing here implies that the flow is actually Reb, so not exactly Reb, it can be reparametrized into a Reb flow. So M phi here is orbit equivalent to Reb an. Yes. So here, that here, I mean, it's not difficult, but here you see that, so it means that it can be reparametrized. Reb an means that the flow preserves a one-form alpha such that alpha wedge d alpha is psi positive. Yes, remember this is the definition here. I say that because here it's easy to see that since here the flow can be reparametrized to a suspension, the suspension can be described as the kernel of a one form which is integrable. So here you can reformulate that by saying that it preserves a one form up to orbit equivalence. It preserves a one form alpha such that alpha wedge d alpha is 0. So here you can rephrase that. Okay. And well, this is the rest. Alpha will be singular. Why? I don't know. No, it's tangent to the foliation. This one here. Sorry, maybe I shouldn't have done that. This corresponds to that case here. Yeah. The suspension case. You see, there are 3 cases. 1, 2, 3. And here this is 1, 2, 3. There is a horizontal correspondence. Sorry. Yes? Okay. And so I think that I will stop here.